All right, so this is hypothesis testing. Chapter 9 is talking about introduction to hypothesis testing and then a couple different tests. To start this out, though, let's review proof by contradiction. Most kids don't remember proof by contradiction, but it kind of goes something like this. If you want to prove that x is equal to 5, for instance, this is kind of a silly example. You start out by assuming that x does not equal 5. And then you go through some logic statements under this assumption, and you come up with some kind of contradiction. Or I should say 2 equals 3, which is a contradiction. So and as long as each of these steps was logically obtained and sound mathematics, if you come up with a contradiction like this must mean that the only possible explanation is that your assumption was false. And if your assumption is false, then that means x does equal 5. It's an indirect proof. And this is kind of similar to what hypothesis testing is. If we want to test the truth of a claimed population parameter, we need to, what we actually want to do is we're going to set up a null and alternate hypothesis. I'm getting a little ahead of myself here, but whatever. This is going to be what we want to prove. So in order to do a hypothesis test, we assume that this is going to be equal to 10. So we assume, again, we want to prove this, so we assume that that's true. It's kind of how we set up a proof by contradiction. And then, under this assumption, if we come up with a contradiction, in other words, if, under this assumption, the probability of getting a sample like the one we get is so small, then it probably didn't happen because of this, rather it happened because of this. Now we've actually set these up and done these simulations before, so it should kind of sound familiar as we work through it. So if we want to assess the truth of a claimed population parameter, for example this, we assume the claim is true and then we take a sample. If the sample is different, and it usually is, right? Our sample is going to be maybe 10.7 or something. If this is different than 10, then there's two explanations. One is that the claim was actually true, and the only reason I got this value was because random sampling. You know, when you take a sample, one sample might be a little bit higher mean and one might have a lower mean. So chance variation in sampling variability. The other explanation is that the mean is not 10, and the reason I got this was because the mean is bigger. Now maybe not 10.7, maybe it's 11, or maybe it's 10.5, but it's happening because it's bigger than 10. So we're going to use probability to determine which of the statements is more likely to be true. We're never going to know which one of these is true. We're going to use probability models to determine whether explanation 1 or 2 is perhaps correct. Okay, and you can read through this if you want here, but in statistics, this formal procedure is called a significance test or a hypothesis test. We called it hypothesis test back in the day. I think now they're kind of calling them significance tests because it determines if you have a significant difference in things, I guess. The first step in a significance test is define the parameter. Exactly the name is the same as we did for confidence intervals, so the P step remains the same. The second step is to identify a null hypothesis and an alternate hypothesis. The null hypothesis is kind of a claim of equality, and the alternate is going to be the claim, is going to be the thing we want to prove instead of the claim. So the null is going to be called the H naught, H sub 0, or H naught, or sometimes I call it the HO, and the HA, or the H sub A, is going to be the alternate hypothesis. These are both statements about a parameter, so we're going to use things like P and mu whenever we set up these HOs and HAs. The HO will be the null hypothesis. It's always got an equality statement, so it's always going to be equal something. The HA is going to be an inequality. It could be a greater than, less than, which is our one-sided alternates, or it could be a not equal to, which is a two-sided alternate. You always choose the alternate before you collect your data. All right. Ricky Bobby is a hotshot basketball player that claims he makes 80% of his free throws. You think he's a liar and doesn't make shots as frequently as he claims. We want to conduct a significance test in an attempt to disprove Ricky Bobby's claim. Define the parameter, the null, and the alternate. So suppose we're making a bet with Bobby. Ricky Bobby, your friend. You say he thinks he can make 80%. You say, no, what? I bet you $10 you can't. So the parameter of interest is going to be P, the true population proportion of all shots of all free throws that Ricky Bobby makes. And then the null hypothesis and the alternate. Now, remember, the alternate is going to be, well, remember, we just went over it for the first time ever, I guess, for you. But the alternate is always going to be the thing you want to prove. I want to prove that the true proportion is less than 80%. If I can prove this, then I win the bet. He pays me $10. So the null then is going to be that P is exactly equal to 0.80. Okay? So there's our null and alternate hypothesis. I run the test under this assumption. I'm going to assume Ricky Bobby makes the shots that he, makes the percentage that he makes. I'm going to collect a sample. And if that sample gives me evidence that this is not true, then I might conclude that this is true. Now it's time to collect data in an attempt to find evidence against the null in favor for the alternate. That's what we want to do. Let's look at 3 possible samples and judge the strength of the evidence they provide against Ricky Bobby's claim. So he takes 100 shots and he makes 82% of them. Well, if this is our bet and this is the results of the after bet, then I'm going to have to pay Ricky Bobby because he actually made over 82% or over 80%. So this is no evidence for my alternate over the null. Yeah, I'm done. I lost the bet. I'd pay him. I'd say, sorry, you're good. You're a good shooter. If Ricky Bobby shoots 100 shots and makes 14% of them, this is overwhelming evidence for my claim against his claim. If he only makes 14% of them, I'm going to see, I told you, Ricky Bobby, you don't make anywhere near 80%. You only made 14%. So I would collect the bet, and he wouldn't have a very strong argument against. But this is the kind of the gray area, and this is what statistics is going to help us decide. If he shoots 100 shots and he makes 78% of them, so this is some evidence. Maybe you could even say maybe it's even weak evidence. I don't know. For my claim over his claim. The issue is like if he makes 78%, then I'm going to say, yeah, I told you don't make 70, you don't make 80%. I should win the bet. And if he's a sensible person, he's going to say, well, I really do make 80% of my shots. I just happen to only make 78% on this because of random chance. If I did this 10 times, I might make 80, I make 82, I might make 83%. But, every once in a while I'm going to make under 80. So my claim is still true. So I'm not going to pay the bet. So the question is, who's right? Who wins the bet? So now we must come up with a way to quantify this strength. No strength, overwhelming strength, some strength. Activity. So we did this in class. Suppose we have Ricky Bobby shoot 50 shots. I don't know why I switched it from 50 to 100 there, and he makes 32 out of 50. So the sample proportion would be 64. So he shoots 50 and he makes 64%. So this is some evidence. Probably pretty good evidence. 64 is quite a bit less than the 80% that he claimed. But again, he still might say, well, it was only 50 shots, maybe, So is this sample proportion of 64% enough evidence to call Ricky Bobby a liar? Let's run a simulation to find out. First, like proof by contradiction, we must assume that Ricky Bobby's claim is true. The null was that he makes 80%. This is the assumption under which the test is run, always. So we're going to assume Ricky Bobby makes 80%. So we did this on the calculator in class, and we kind of created a dot plot of simulated sample proportions. But let's just, if we flip to the next page, we'll see kind of a computer-generated output of that same excuse me, simulation. So first of all, there are two explanations why 64% of the shots were made when the claim proportion is 80%. What are they? Number one, Ricky Bobby really makes 80% of his shots. This sample was low due to sampling variability. Meaning he really makes 80% of his shots. This just happened by random chance. He had a bad day. Number two, Ricky Bobby doesn't make 80%. And really makes under 80%. I guess that was a little bit repetitive. I could have shortened that up, but and we got 64% because of this. Sorry, that's not perfectly worded, but you get the idea. So we need to figure out which one of these is a more likely, a more probable outcome. So what I did was I simulated 400 shots under the assumption that he really does make 80% of his shots. Always assume the null is true. So as you can see, most of them were right around 80%. About half of them were higher and half of them were lower, as you would expect. And there's variability. But what this does is this gives us a picture of the amount of variability there is when he shoots 50 shots. Just a reminder, what is this thing? Each of these points is a sample proportion. What do we call a collection of sample proportions? This is a sampling distribution of p hat. So we just studied those, right? Or studied them twice now, I guess, 2 chapters in a row. So this is a simulated sampling distribution of p hat. We could also come up with a theoretical sampling distribution of p hat. We should know how to do that. But notice the 64% is right there. So if the null is true, so assuming this is true, use the larger simulation to the right to find the probability that we would get a p equal to 64% or less. So this is a probability that your sample proportion is less than or equal to 64% given the true proportion is 80%. So this is a conditional probability. So out of 400 trials, how many of them were 64 or less? There were 3. What is that? 3 out of 400. 0075. So less than 1% chance that would happen. This is called the p-value of the significance test. The p-value is the probability computed under the assumption that the null is true, that the statistic would take a value as extreme as or more extreme than the one we actually observed in the direction of the alternate. Okay, so what does this value tell us? This gives us the probability that this right here happens, right? Given the null is true, how likely is it that we would get a sample like the one we got, or even more extreme than the one we got? And the chances that happening is less than 1%. So now Ricky Bobby could make his argument. He could say, I told you it could happen. It's possible that I get a sample this small. And you say, well, yeah, it is possible, but it happens less than 1 time out of 100. So are you going to tell me that this one time that we bet on this and we did this was that 1 out of 100 thing? No, that's not what happened. I think because this is small, I think this is not why you hit 64%. Therefore, I'm going to conclude that you really make less than 80%, and that's why you hit 64% of your shots or less. And that's basically a hypothesis test. Note the p-value is a conditional probability. All right, I'm running out of time here. I'm going to have to stop this video and pick it up on the next go around. So we'll pick it up here on the next one, okay?